You're tuning in for another deep dive, and today, well, we're jumping into something pretty crucial in the world of large language models.
Yeah, we're looking at how to make these really smart AI systems smaller and faster.
Exactly. But crucially, without them losing their smarts. And we're focusing on a specific new approach called task circuit quantization. You'll hear us call it TaCQ.
Mm-hmm. TACQ.
We've got some really interesting research papers here, quite academic, that dig deep into this.
They really do. It's dense stuff.
It is, but our mission here, our goal for this deep dive is to unpack all of that. We want to give you a shortcut, really, to understanding how TACQ works, why it's considered innovative, and, what it could actually mean for using LLMs in everyday life.
Right. Let's get into the core challenge first. Why do we even need to shrink these models?
Good question. I mean, these big models are powerful, but they're big.
Exactly. They take up a ton of memory. They need serious processing power. That makes it really hard to, say, run on your phone or your laptop.
Right, or even on like smaller servers sometimes. And then there's the speed issue latency. Plus, sending your data off to some big cloud server raises privacy questions for a lot of people.
Definitely. So compressing them, making them smaller and faster opens up all these possibilities for local use, better privacy, quicker responses.
And that brings us to a key technique people already use, right? Post-training quantization, PTQ.
Yes, PTQ is sort of the go-to method. The basic idea is you take a model that's already been fully trained.
So you don't have to do the expensive training part again.
Correct. And you convert its weights. These are just the numbers that represent connections inside the model. You change them from high precision numbers, maybe 16-bit floating point, down to lower bit numbers.
Like 8-bit or 4-bit or even lower.
Precisely, like 2 or 3 bits. And doing that after training saves a massive amount of computation compared to retraining.
Okay, sounds great. Smaller model, faster processing. What's the catch?
Well, the catch, especially when you get really aggressive, like down to those 2 or 3 bits, is performance. The model just doesn't perform as well.
It loses accuracy, becomes less smart.
Yeah, you lose a significant amount of information. Think of it like trying to represent a really detailed photo with only a few colors. You lose nuance, you lose detail.
Okay, so that's the big problem with standard PTQ at very low bit rates.
It is, and people have tried things to fix it, like mixed precision, quantization.
What's that?
That's where you say, okay, maybe some weights are more important than others, so let's keep those important ones at a higher precision, maybe 16-bit, and quantize the rest more aggressively.
Ah, okay. So it's not uniform quantization anymore.
Right. But the tricky part is figuring out which weights are the important ones, and that's where TCQ comes in with arguably a much more targeted, theoretically sound way of identifying them.
Interesting. So TCQ builds on this idea of mixed precision, but does it differently.
Exactly. It's really inspired by research into how these LLMs actually work internally, like understanding where knowledge is stored.
Oh, like interpretability research. Try to peek inside the black box.
Precisely. There's this growing understanding that knowledge isn't just, smeared evenly across the whole network. It tends to be localized,
Localized, meaning,
meaning specific parts of the network, specific connections become really important for certain tasks. This connects to another idea called automated circuit discovery, finding these mini networks or circuits inside the bigger LLM that handle specific functions.
okay, weight circuit. Let's unpack that a bit. So the idea is if the LLM is doing something specific, like answering a question,
Right, or maybe translating text or writing code.
only a small subset of all its millions or billions of weights are actually like critical for that specific job.
That's the core hypothesis. Yeah, these interconnected weights form a kind of task-specific circuit.
Like wiring in a house. You only need certain wires active to run the microwave, even though the whole house is wired up.
That's a great analogy. TaCQ-'s innovation is that it tries to find those critical circuits for the task you care about, and then it treats those weights differently during quantization.
How differently?
It aims to keep those really important task-specific weights at a higher precision, say 16-bit, while quantizing the rest, the vast majority, much more aggressively down to 2 or 3 bits.
Ah, okay. So you protect the crucial stuff and compress everything else heavily. The goal being high compression, but keeping performance high for that task.
Exactly. Minimum added memory costs for protecting those few weights, but maximum performance preservation.
So how does TaxiQ actually find these important weights? What's the mechanism? You mentioned a saliency metric.
Yes, the secret sauce, if you will, is this novel saliency metric they developed. It's designed specifically to figure out which weights matter most for a task and are most likely to be messed up by quantization.
Okay, and this metric has different parts to it.
It does. It cleverly combines two distinct components. The first is called quantization-aware localization, or QAL.
Quantization-aware localization, QAL, what's that measuring?
QAL tries to estimate directly how much quantizing a weight is actually going to change its value and impact the model.
How does it do that?
Conceptually, it compares the original model, the clean one, with a version where all the weights have just been uniformly quantized, the corrupt model.
Okay, so it looks at the difference between the original weight value and what it would become if you just crunched it down.
Right, that gives you the potential disruption caused by quantization for that specific weight. But QAL doesn't stop there. It multiplies that difference by the gradient of the loss function with respect to that weight.
The gradient that tells you how much changing that weight affect the model's error, right? Its overall influence.
Exactly. So the QAL formula is essentially gradient times original weight, quantized weight.
Okay, let me see if I get this. It prioritizes weights that are both very influential, high gradient, and get significantly changed or distorted by the quantization process itself. Big difference.
You got it. It pinpoints the weights that are simultaneously important and fragile under compression.
Makes sense. So that's QAL. What's the other component? You said magnitude sharpened gradient, MSG.
Yes, MSG. This provides a more general measure of a weight's importance, kind of independent of the quantization effect itself. It's adapted from techniques used to figure out which parts of an input are important for a model's decision.
Okay, so how does MSG measure weight importance?
It's simpler, actually. The formula is just weight value times gradient.
So it looks at how big the weight's value is and how much impact it has on the loss.
Right. The intuition is that weights that have both a large magnitude and a large gradient are generally pretty crucial for the network's function.
Why include both QAL and MSG? Why not just use QAL since it seems so specific to quantization?
That's a good point the researchers addressed. They found that relying only on QAL sometimes missed things. For example, a really important weight might just happen to be very close to a quantization level.
So the original quantized difference would be tiny, even if the weight was super important overall.
Exactly. QAL might overlook it. MSG acts as a sort of safety net, ensuring that weights that are generally significant, large magnitude and gradient, are still flagged, even if quantization doesn't change their value much.
I see. It provides a baseline importance measure. So how are QAL and MSG combined in the final TaCQ saliency score?
It's actually the product of all the components we discussed. So the final score is like weight value times gradient times original weight, quantized weight.
Okay, so it multiplies the general importance, MSG part, with the quantization sensitivity, QAL part. It's looking for weights that score high on both counts.
Precisely. Those are the weights TaCQ flags as most critical to keep at higher precision.
And calculating this requires running the model on some data, a calibration data set.
Yes, it needs a small data set to calculate these gradients and quantization effects. And interestingly, the research shows you can use a general data set, or
You can use data specific to the task you ultimately want the model to do well on.
exactly. And using task-specific data helps TaxQ zero in even better on the actual circuits needed for that task, leading to the best results.
Right, that makes intuitive sense. Okay, so that's the theory. Identify critical quantization-sensitive weights using this combined QAL and MSG metric, protect them, and quantize the rest. How well does it actually work in practice? What do the results show?
Well, the results presented in the paper are, frankly, quite impressive. They tested TaSQ against other leading mixed precision methods like SPQR, SqueezeLM, SliM-LLM.
Okay, some well-known techniques.
Right. And they tested across different tasks, question answering, math reasoning, even tricky stuff like text-to-SQL generation.
And different models, too.
Yep, modern architectures like Llama-3 and Qwen2.5. And the consistent finding was that TaCQ performed better, especially, and this is key, in those really aggressive 2-bit and 3-bit ranges.
Those ranges where models usually fall apart. How much better are we talking?
Significant. In the 2-bit setting, which is extremely challenging, TaCQ averaged about 14.7% higher accuracy than the next best method, SliM-LLM.
Wow, almost 15% absolute improvement on average at 2-bit.
Yeah. And on specific tasks, it was even more dramatic. Like on GSM-8K, a math benchmark, it was nearly 16% better. On the Spider text-to-SQL task, get this, over 21% better accuracy.
21%, that's huge at such low precision.
It's massive. Even on the broad MMLU benchmark, it showed over 14% gain at 2 bits. These aren't small increments. They suggest TaCQ is fundamentally better at preserving capability during extreme compression.
That's really compelling. Did they confirm the benefit of task-specific calibration data?
They did. Using task-specific data definitely pushed the performance higher, confirming that TaCQ can tune into those specific circuits. But importantly, even using general calibration data, TaCQ still beat the other methods significantly.
So it's robust.
It seems so. Like on one MMLU subtask, it still gained over 7% at 2 bits compared to SliM-LLM, even without task-specific tuning. It suggests the saliency metric is good at finding generally important weights too, not just task-specific ones.
Any other advantages mentioned? Practical ones?
Yeah, a couple of nice points. One is usability. TaCQ basically has one main knob to turn. What percentage of weights do you keep at 16-bit?
Ah, so it's simpler to configure than methods where you might need to figure out optimal bit widths for different layers or something?
Exactly. Much simpler control over the compression versus performance trade-off. And they also did ablation studies, testing parts of the method in isolation.
To see if both QAL and MSG were necessary.
Right. And they confirmed that yes, both parts contribute significantly and using them together works best. Neither one alone was as effective.
What about specific model results? Anything stand out with Llama 3?
Oh yeah, the Llama-3 results were pretty striking. They managed to get the Llama-3 8B instruct model quantized down to an average of just 3.1 bits per weight to perform at 96% of the original full precision model's accuracy on MMLU.
96% recovery at 3.1 bits. That's incredible. How did that compare to others?
That was over 5% higher absolute accuracy than SPQR could achieve at a similar compression level.
Wow. And you mentioned the spider text-to-SQL task earlier.
Yes, that was another really interesting finding. At the super compressed 2-bit level, TaCQ is basically the only method that gave any meaningful results at all. The others just kind of collapsed.
What does that suggest?
It suggests TaCQ is much better at preserving the model's ability to generate complex, coherent outputs, not just, pick the right answer from a list. That's crucial for generative tasks.
Okay, this is all sounding very promising. Let's connect it back for the listener. We've gone through the tech, the results. Why should someone outside of AI research labs care about TaCQ? What's the bigger picture impact?
I think the implications are genuinely exciting. We're talking about enabling really powerful AI to run directly on your devices.
Your phone, your laptop.
Exactly. Imagine having near full performance LLM operating locally. That means faster responses because there's no network lag. It means better privacy because your data doesn't have to leave your device.
That's a huge deal for many people.
It is. And it also means we could put sophisticated AI into devices with limited power or connectivity. Think edge computing, robotics, smart sensors, things like that. TaCQ is a significant step towards making that practical.
So faster, more private, more accessible AI. That's the potential payoff.
Absolutely. And there's another layer too. Understanding how TaCQ works, how it identifies and saves this crucial information, actually teaches us more about the LLMs themselves.
How they organize knowledge.
Yeah, how they structure information for different tasks. These insights could fuel the design of entirely new, even more efficient AI architectures down the line.
So it's not just about shrinking existing models, it's also about learning how to build better ones in the first place.
Potentially, yes. And the research also points to remaining questions like why tasks involving generations seem more fragile to quantization. There's still more to figure out, more innovation to come.
Okay, so wrapping up this deep dive on task circuit quantization, what's the main thing we want listeners to take away?
I think the key takeaway is that TaskQ represents a really smart, task-aware way to compress these giant language models. It's not just brute force shrinking. It intelligently figures out what information is most vital for a specific job.
Using that clever saliency metric with QAL and MSG.
Exactly. And by protecting that critical information, it achieves much, much better performance at very high compression rates, especially those tricky 2 and 3 good levels than we've seen before. It's a big step forward for practical AI.
Definitely. And hopefully this discussion has given you, our listener, a good handle on what TaCQ is, why it's innovative, and the kind of future it might help unlock.
Which leads us to a final thought for you to chew on. Really consider this. What happens when you have LLMs running at nearly their full capability right there on the devices you use every day?
Locally, privately, instantly.
Right. What new things become possible for you? What apps, what interactions, what conveniences? How might that fundamentally change how you use technology in 10 years? Something to think about.